It's ExplainerCast episode 10. I'm your host, Dave Smith.
And this is Shane Swenson.
And we have some explaining to do. Today, we are starting another saga. We actually already have one ongoing, yet to be completed saga about telecommunications.
Yep.
And this, we don't know how many parts that's going to be yet.
That's right.
And today, we are starting another saga because there's really not too many sagas you can have running at the same time.
Or we'll find out.
We're going to start another saga. Yes. We're going to learn what the maximum number of concurrent in-progress sagas is.
Yep.
But hopefully it's not 2 or 1. Anyway, so today we're going to start a new saga on how computers work. And our goal here is to go to the very fundamental levels of how computers came to be.
Yep.
We're not really going to cover the history so much as how they actually work. And then we're going to go into as much depth and breadth as we can over the coming episodes. But today we're going to start at the very, very basics. I guess you could say the atoms of the computer, but not really atoms.
Atoms and electrons.
Of how they work. Yes. There certainly atoms and electrons are involved. And we will probably talk about some of that. But yes, the very fundamentals are what we're going to cover today. So with that, let's jump in.
Sounds good. And yeah, there's a line between, I'll say, computer people and electronics people, perhaps, and that's probably when we talk about the fundamentals, that's probably where we're going to settle, is just above that line. Below that line, you really have to understand how electricity works in really fundamental ways, and the answer is it's really complicated. And so most computer people try to sit well above the line where they can think about very more simplistic models where there are ones and zeros in the world, which might be represented as electricity flowing or not flowing, so current on and off, or voltage high, voltage low, you're using switches and things like that, and not really worry about the atoms and electrons. So I think from what we would call an abstraction perspective, that's the approach we should start with.
Absolutely. And I think ones and zeros is where we'll begin, understanding that there's many ways to represent them. But given a universe that has ones and zeros in it, what would you say, Shane, is the most fundamental building block of a computer that operates on ones and zeros?
Yeah, so at the fundamental level, and maybe we'll just dip a little bit below. So back in the Moore's Law episode, we talked about integrated circuits and the components that were being integrated on that circuit. And the fundamental component that we mentioned is something called a transistor. And so I guess if I wanted to have a perfect representation of a 1 and a 0, what I would really want is I would want an electronic switch, like a light switch, so that I could say in my living room, when the switch is up, the lights are on, and when the switch is down, the lights are off. And I would say the on state is a 1 and the off state is a 0. And now I have a way of storing that value by flipping the switch, and I have a way of observing that value by looking at the state of the lights. And so in a computer, we'd like a way to represent an on or an off some way, really a 1 or a 0. And then we want to be able to set those values, measure those values, and ultimately perform computation or make changes to our data and our systems based on those values.
And the data, I should say, the data itself is also just collections of ones and zeros.
That's right. Yeah, we're going to, and what these are called digital computers, digital meaning digits referring to numbers. And computers have a very simplistic model of this, which is there's only 2 numbers that matter, 0 and 1. And so this is called the binary system, as opposed to the base 10 system that we human beings tend to live in, which is where more conventional digital systems that we think of are where you have digits from 0 to 9 representing 10 different values. In a computer, there's only 2 states typically, the 0 and the 1. And then the way that the computer can handle large quantities of information is it has lots of ones and zeros to deal with, as opposed to having more unique digits.
Exactly.
So what we'd like would be a way to take ones and zeros. So we'll talk later about really any numeric data, any integer-based data, any value that can be represented as a whole number. So a number that doesn't have a fractional part, can be represented in our world as digital, as a base 10. So like if I was going to write the number down on paper, I'd write it down in base 10 using the digits from 0 to 9 with place sequence. That can also be converted into binary, which is a sequence of zeros and ones. And we can talk maybe later about how that's done. But fundamentally, to the computer, the information it's processing as data is going to be turned into a set of zeros and ones. They'll be input in some way, they'll be stored in some way. And again, we'll want to perform modifications on those.
And let me just say, Shane, I said we weren't going to go into history, but it's worth noting that some of the early computers, like I'm thinking of the famous supercomputers, well, the company that turned into a supercomputer company that was founded by Seymour Cray, that literally the input for the early Cray computers were switches on the front of a panel.
Yeah.
Where you could switch, there was like 8 of them or something.
Yep.
And Seymour Cray himself would just set them into certain positions, on, off, on, etc., that had different representations to the computer. And that was the input. So like when you say light switch on, off, like literally that's how the first computers were, or not the first, but that's how many early computers operated.
That's right. Yeah. And there were other manufacturers that did similar things. And essentially they give you this panel of switches and you would set them to different configurations. And then there would be usually a mechanism to store that into the computer and then to set a new configuration of switches and then store that as an additional piece of data in the computer.
And this is a useful thing to think about because at the very fundamental level, this is what your computer is doing, although it's not doing it with physical switches anymore, and it's not doing it with lights. And I want to mention that the input might have been switches, and then the output would be a series of lights that would be on or off that would tell you what the computer's result was.
Right. Yeah. So a very direct representation. And so, for example, if I had a simple operation to add 2 numbers together, you could imagine using this system where you put the switches in the binary configuration that represents the first number and you store it. And then you put the computer in the binary configuration that represents the second number and you store that. And then you execute the program on the computer that adds these 2 numbers together and then displays the result by lighting the lights in sequence where every 1 in the answer in binary would have a lit bulb and every 0 would have an unlit bulb. And now you could read the answer back out. And this isn't a very interesting computer program, but starting with very simple operations like that, then modern computers essentially have a very large number of instructions in the program and a very large quantity of input data they can process very rapidly to generate outputs that might either be raw data, maybe a document, perhaps a representation on the screen of that information. So now instead of lighting a series of bulbs on a panel, we're lighting all the individual pixels or colored light picture elements that form a grid on your screen. And this is just done at a much higher rate than we're talking about in these old computers, enabling the modern applications that we interact with today.
So should we go into how the computer takes those inputs and produces outputs and what we generally call digital logic?
Yeah, let's go really simple here now that we've kind of set the stage. And then over time, we can talk about some of the more complex operations. So the fundamental thing that you want in this computer is an electronically controlled light switch, essentially.
Mm-hmm.
Something that can take an input that is in the digital logic representing either a 1 or a 0, and then measure it, and then produce an output based on that measurement.
And when you say measure it, you mean very simply determine if it was a 1 or a 0.
Yeah.
We're not talking about a numerical measure from 0 to 100 or something. It's just, is it a 1? Is the input a 1 or is the input a 0? And do something based on that.
That's exactly right. Yeah. So in our current model, imagine I'm the computer and I say, well, if I see that the living room lights are on and that's a 1, I'm then going to turn the kitchen light on and have that mimic. Or I could have a different operation that says, whatever I see in the living room, I'm going to do the opposite. So if it's on, I'm going to turn the kitchen light off. Or if it's off, I'm going to turn the kitchen light on. And so I'm observing the state of one bit of information, and then I'm making a choice about how to set the state of a different bit of information. And so the computer needs to be able to do the same thing. it needs a way to, based on one value for a bit, one or more, we'll find we need operations that work on at least 2 bits in order to do really interesting things, produce then a third bit of output that is based on the states of that 1 or 2 input bits.
And it's probably worth noting here that the word bit is actually an abbreviation for the term binary digit.
Yes. Yeah. So again, a single 1 or 0, we call it a bit, and we're going to use that term a lot. So
Yeah,
it's important.
we might use it a bit.
There you go. Yeah. Nicely done. So the key electronic element that enables this ability to take an input value and produce an output that is based on that input value is something called a transistor. And I think we talked about transistors back in the Moore's Law episode. And a transistor really has three important elements. It has what's called a source and a drain and a gate. And the basic way to think of a transistor is it's an electronically controlled switch. So it has the ability to allow electrical current to flow from the source to the drain. And so you give it a high voltage at one of those points, and you give it what's called a ground connection at the other. Different computer chips use different voltage levels for their logic. And then based on which voltage is applied at the gate, that current will either flow or be blocked. For example, you might have a transistor where the current is blocked if the voltage at the gate is 0, but the current can flow if the voltage is at the high setting, say that 5-volt setting. Okay, so these devices called transistors are often called a field effect transistor because they rely on the electric field coming from the gate to control that flow of electricity. And you can make, with different materials, transistors that have different properties. And so it's often quite common that the drain is the higher voltage and the source is actually connected to ground. It can go either way. And similarly, there are some where the gate voltage being equivalent to the source will enable the current to flow, and in some cases where that will stop the current from flowing. So you could think of it as a switch that defaults to on or a switch that defaults to off. And so in this transistor, the thing we're measuring is going to be the voltage that's applied to the gate, and the result of that is going to either be that the current between the source and drain is blocked, in which case if you were to put a resistor in line with that source to drain connection and measure the voltage across it, you would have a low voltage. Or when the current is flowing, then you'll get current flowing through that resistor and you'll get a voltage drop across the resistor, which can then be used as your output. So you'll either get, based on a low or high input voltage to the gate, you'll either get a low or high output voltage, depending on the type of transistor you've set up. But you now actually have created an electronically controllable switch.
Exactly.
Where the switch is controlled through the gate and it's measured by the flow of current from the source to the drain, or vice versa.
And then, as computer programmers think about this, they don't care at all about whether it's high voltage, low voltage, or
right.
Default on, default off. All they think about is there's a 1 coming in, and when a 1 is coming into the gate, then a 1 comes out, or whatever the logic is.
Exactly. So this is something that the electronics engineers have to think a lot about, which is what is the exact voltage and what are my thresholds and how long do I have to wait from the time that I provide a change of voltage at the transistor gate until it's measurable as the current flow between the source and the drain. They have to worry about all those things. Programmers really want to think in pure ones and zeros and trust that the engineers who designed and built the circuits used by the computer are translating all of that analog electronics into ones and zeros.
Yeah, and I'll just add, like, if you're having a kind of a question of how big are these things, They are microscopic. You cannot see them with the naked eye. They are so small now.
Now they are.
Now they are. Now, having said that, of course, there are big versions of this. You could imagine a switch that literally does the same thing.
Yep.
That's electrically controlled. But nowadays, these things are crammed. I don't know if it's millions or billions.
It's at least billions.
Yeah, onto these tiny things that are smaller than a postage stamp, one layer deep, very thin layer of these transistors. But they are tiny and they are very, very fast, meaning that they can switch from an on-off state literally billions of times per second.
Yep.
And so you can move a lot of ones and zeros through them.
That's right. Yeah. And when we start talking about computers, often a computer has a clock speed, and that clock speed is measuring how fast the entire chip needs to change from one state to another, including the possibility that we'll start talking about where a series of these transistors are cascaded together. And so a single computer processing step results in millions at this point of transistors changing their states, millions more measuring those states and changing something else on downstream until they produce the new computation result. And that happens billions of times per second.
It's incredible.
Think 2 billion times per second in current clock speeds.
Yep.
And so when we talked about Moore's Law, we talked about this exponential scaling and how computers started with really switches manipulated by hand. Some of the early electronic switches and transistors were built in what were called vacuum tubes, which looked like small light bulbs. And then they became standalone electronic components made out of silicon using what are called semiconductors. And then the integrated circuit was putting lots of those silicon transistors onto a single silicon chip. And then we talked about Moore's Law, which was this exponential increase every year or two in the sheer number of these elements on each chip. And corresponding to that was a reduction in the size of each element. And so I just saw there was a new product release from a major computer manufacturer, and they were talking about how they're now using a 3 nanometer process for their latest chips.
Man.
And that means,
oh my goodness,
like the size of an individual element, like the width of the gate on one of these transistors is 3 nanometers ish. And I mean, that's not that many molecules of silicon. It's crazy.
Yes, it's crazy. And what's really crazy about this, and after this we should probably shift to digital logic and how we actually build computers out of these things, but is they are incredibly reliable. As I've been doing software development for 20 years, and I have never once encountered a situation where my software misbehaved because one of these transistors wasn't doing its job right, the hardware.
Mm-hmm.
And when you think about how they are changing state billions of times a second, and there are millions and millions or billions of them on a chip, and they all have to work for the results to be right. And then you think, how many times would you have to turn the doorknob on your door before it would wear out and fail? I'll bet you couldn't get a billion turns of that doorknob before the parts start falling out of it.
Yeah.
But these transistors, a billion times a second, second after second, month after month, they just keep working. And I'm sure they can fail, but my goodness, is it rare?
Yeah. Yeah, they go for years at that rate. And so if you were to think about the failure rate, 1 in I don't know how many trillion, quadrillion, or whatever, how many zeros in the denominator.
Huge.
And then at the current scale, though, there are a couple things that can go wrong. And that is that 3 nanometer component is so small, there are actually not that many electrons, or I don't know if I want to get into the alternative to electrons, but there aren't that many charged particles moving across that gate. And they're close enough together that the source and drain on either side of the gate, you can actually have quantum effects where they just hop to the other side. And so there are opportunities for errors more at this tiny scale than there used to be. And people also talk about gamma rays, like a very highly energized photon that hits the chip and flips something. And this can happen. And so typically these very high-end circuits do now have error detection and correction built into them just to get that last bit of reliability and to catch that, even if it's very infrequent in terms of operation count, there's so many operations happening and they're so detrimental to a computer program because as programmers, like you said, we assume that a 1 is a 1, a 0 is a 0, and always will be. And we don't typically layer error correction unless we're doing like long distance communications or something like that within the computer.
Yeah.
We assume that things are going to be correct. And so we do rely on some error correction built into the hardware to achieve that. But it's still remarkable.
It is crazy remarkable. Okay, so how do we put these things together to actually make digital logic? And digital logic is the term that we use to describe now one layer of abstraction higher than the electrical, physical, mechanical layer, which is how do we actually string these things together conceptually to create useful programs that do things that we want.
Yeah.
It's been quite a few years since I've studied this field, but I would propose there are three fundamental elements that can be built from transistors that constitute all digital logic. I'm going to take a shot at that, Shane, and then can you correct me where I go wrong here?
Yeah, let's go for it.
So we call these things gates, and you can think of them as units that either allow a 1 to pass through as a 1, or a pair of 1s and 0s or bits to pass through and then read a result at the end. And there are three of them. There's an AND gate, an OR gate, and a NOT gate. So an AND gate takes 2 bits as input and produces 1 bit as output. And the reason it's called an AND gate is because in order for the output to come out as a 1, the 2 input bits must both be 1, meaning 1 and 1, then you get a 1 on the output. So that's an AND gate, and we'll talk about how that's useful later. But now let's talk about an OR gate. So an OR gate is kind of, it serves a similar purpose to an AND gate, but it has different rules. It also has 2 input bits and 1 output bit. But with an OR gate, either one of the input bits or both have to be a 1 for the output bit to be a 1. And in fact, the only case where it will be a 0 output is if both of the inputs are 0, the input bits.
Yep.
And so you can think of an AND gate and an OR gate as they're very, very similar, but they have different logic. And that's why we call this logic, where you're saying if this and that, then 1.
Yep.
Right? And that's what AND is. And then OR is if this or that, then 1.
Yep.
And when I say if, I mean like if this is a 1 or this is a 1, then the output is 1. And then the final logic unit is called a NOT gate, which simply takes a 1 and turns it into a 0, or takes a 0 and turns it into a 1.
That's right. And so that one you can think of as actually quite simple. You could probably even think of how you would build it, because we talked about our transistor that has a gate, and depending on the voltage applied at the gate, you'll either get current between the source and drain or not. And so a NOT gate essentially says, if I give a high voltage to the gate, then I want a low voltage to come out of the transistor, meaning no current between the source and the drain. And if I give a low voltage to the gate, then I want a high voltage to come out, which means I want it to open the to close the switch, let the current flow, so I get a high voltage coming off my measurement of the current between the source and drain. So the NOT gate is actually quite simple to implement. And the AND and OR are similarly not particularly complex in their own right, but once you have these gates available to you, you can now construct much more complex operations by combining them in sequences and connecting some of their inputs to other outputs, or so the outputs to other inputs, I should say.
And I think right now maybe we could talk about one example of those, let's call them machines that you can build out of these digital logical components. And I actually would like to talk about an adder.
Yeah, let's do it. That sounds great.
So doing addition is like the first mathematical operation that I think people think of when they think of their calculator or a computer. Actually, I mean, the first thing I think of on a computer is like watching YouTube videos or something.
But there's lots of adding in that.
Yeah. Lots of arithmetic to get a YouTube video. But the beauty of doing addition on a binary computer is that the number of different input states you need to consider is actually very small. If you want to add 2 bits together, meaning 2 binary digits together, the total input space is very small. You can add 0 and 0. Well, the answer to that is 0.
Yep.
Easy. You can add 0 and 1. The answer to that is 1.
Mm-hmm.
Or you can add 1 and 1. And the answer to that is actually 0, but carry the 1.
Yep.
1 plus 1 in binary is actually 10. I mean, we would write it as 1, 0. is the addition.
Yes.
And so an adder, a binary adder for a single binary digit just needs to take as input 2 binary digits, 2 bits, and it needs to output the sum of those 2 bits, I should say,
Yep.
and a carry bit, meaning that if you had the 1 plus 1 case, you need to be able to communicate to the output that, yes, this summed up to 0, but there's a carry bit that you need to know about if you're actually going to represent this number.
Yep, exactly.
So how could we put this together? And I have not done this in years. I have not thought about how to build an adder. But in college, we did construct these things out of gates in a simulator, and it was really fun. But essentially, when you think about all the different cases, there's not that many to consider. Like I said, so 0 and 0 needs to give you a 0.
Yep.
Well, an AND gate does that.
Right.
A 0 input and a 0 input gives you a 0 output. That's perfect. And an AND gate, but an AND gate it breaks down when you have a 0 and a 1 because that will also give you a 0 output, and it shouldn't. That should give you a 1 output. So you got to now combine AND gates and OR gates together so that like the output of the AND feeds the OR, and then you take a copy of the input and send it to the OR as well, and then you can start to piece these together. Now that's not exact. I'm not actually doing this justice, but you can start to imagine where you take copies of inputs and send them to peer gates that are also taking outputs from the first gate as one of its inputs, and now you can start to combine these things and see how you can add ones and zeros together to get an output.
Yeah, and this is where there end up being some ways to think about digital logic, and this was called Boolean logic because a mathematician, last name Boole, codified some of the rules of how you can combine different binary operations to produce others. And there are actually a couple others that we didn't talk about yet that have names. And one way that I think about these is what's called a truth table, where you make a little grid and you have your 2 input bits, and each of them could be a 1 or a 0. So on one axis of the grid, you put one of the inputs 0 or 1, and on the other axis, you put your second input 0 or 1. So you've now got 4 possible outputs that you want to measure in this little grid. And then in each of those grid squares, you put what you expect. So Dave, you described an AND gate, which is 1 only if both inputs are 1 and the other 3 states are 0. Mm-hmm. You described an OR, and I'll be clear, this is what's called an inclusive OR, which means if either or both of the inputs are a 1,
right,
you get an output that's a 1. And so the only state that outputs a 0 is with both inputs being 0. There's another kind of OR called an exclusive OR, and it's sometimes written as XOR or XOR in the arithmetic. And an exclusive OR says a 1 will come out only if one of the inputs is a 1 and the other is a 0. And the order doesn't matter. So either could be a 1, the other must be a 0, and then you'll get a 1. If both are 0 or if both are 1, then you're going to get a 0. And so the first digit of the adder that you want to produce is actually an exclusive OR. And one way to build that is you could say, well, it's a 1 if either input is a 1, so that sounds like an OR,
mm-hmm,
and not both inputs are 1. And then I get an OR.
Exactly.
Then I get my exclusive OR. And so you end up using an OR gate, a NOT gate, and an AND gate, and you can construct this, and maybe there's a second AND gate involved. And there's also something called a NAND gate, a NOT AND, which essentially is the inverse of the AND. And so as you have some of these others, it becomes a little easier to build these circuits. But yeah, as you described it, is really how it works. It's really just a collection of these very simple gates that produce the correct output for each possible combination of inputs, just fully defining what the operation is.
Yep. Super cool. So you can see, like, from that, from what Shane just said, an XOR gate is an adder, but it doesn't have the carry bit.
Right. So then we'll make a copy of those 2 inputs and we'll compute the carry bit. And so let's see if we can, in real time, describe the logic for the carry bit. Why don't you go, Dave?
Yeah, so the carry bit, we already said, like, 0 plus 0 equals 0 with no carry bit.
Yep.
1 plus 0 equals 1 with no carry bit. So that leaves only 1 plus 1 that would yield a carry bit. And so what is one gate that only gives you a 1 when both inputs are 1? Well, that's a simple AND gate.
Exactly.
So the simplest, what that means is that we can boil an adder down to 2 gates, an XOR for the sum result,
yep,
and an AND gate that takes an exact copy of the two inputs for the carry bit. Now, you have created a binary adder out of just these two simple components.
Yep. And then if you want to add multi-binary digit numbers, you just have to do one more thing, which is for all of the places after that lowest bit, you need to now have a 3-digit adder because you have the two input digits, 0 or 1, plus you have the carry bit.
Yep.
So the logic gets a little bit more complex, but it's still very doable with a couple of gates in sequence. And you essentially ripple these from the least significant bit, the ones position, on up through the more significant bits step by step.
Which is really cool because you take the carry bit output of the first bit adder and you wrap it around and take it in as an input to the next bit instead of taking another raw bit in as input because it has to now be added with the next bit. In the same way you carry a number when you're adding on paper in decimal.
Yep.
You have to wrap that bit around and it becomes the input to the next one. And you can stack these up as much as you want. And most modern computers, including probably the computer you're listening to this podcast on right now, they do 64 bits of integer arithmetic, meaning that they've got 64 of these XOR and ANDs piled up next to each other with the carry bits wrapping around from all of them except for that very last one. It just goes out into, I don't know what they do with the carry bit off the 64th adder component.
Either you do a wraparound or an overflow, depending on the type of operation you're trying to do.
Yes. Whether you want yes, good point. That's probably a little bit too much depth. But that kind of gives you a sense for like, oh, you can actually add huge integer numbers now because 64 bits of ones and zeros allows you to add numbers that have a huge number of digits in decimal, like 20-digit numbers in decimal. Can be expressed in 64 bits of binary.
Yep. Yeah, you would be a 64-bit number. Yeah, it's very huge. Maybe we'll talk about binary next time or another time. I don't want to go into too much detail there.
Yeah.
So one last thing just I was going to throw out on the logic is the Boolean logic has very specific meaning for and, or, not, and XOR. And sometimes, because there is an English word, it sometimes catches us off guard. When human beings in English, when we say, would you like French fries or a salad? If you say yes, you're doing an inclusive or, which probably isn't what the other person expected. We don't say, would you like French fries exclusive or a salad, XOR a salad? But that's often what we mean.
Honestly, we should. I would love it a lot more if we did.
Yeah, I'm sure it would definitely get us invited to lots of social gatherings if we start doing that.
I don't know, Shane. Do you want to go to this party, XOR that party?
Well, there you go.
We have so many to choose from, but we can only choose one.
Well, all I have to say is yes, I do. Choosing is a whole different matter, isn't it?
Exactly.
All right. Well, there's a lot more to talk about with computers, but I wonder if this is a good place to wrap up for today.
Yeah, we'll pause here. So in review, we've covered some of the fundamental electronic phenomenon, just very briefly touched that, but also got our feet wet with digital logic and how you can combine these digital logic elements that we usually call gates to create useful features. And today we just talked about one, which is adding numbers together to get results.
Yep.
But we can create a lot more features. And I think in the next episode of this saga, we will carry ourselves forward into some really cool stuff, including how do you store information like that? Because right now we just talked about information that flows through these gates, but it turns out you can arrange them to store information too, so that you can then access that information later, and then that can be an input to other sets of gates. And it just goes crazier and crazier from there. It turns out the fundamentals we talked about today can be applied to do pretty much everything that we do with computers.
Absolutely. Well, that sounds super fun. I am looking forward to it.
Me too. Thanks a lot, Shane. This has been another great episode of ExplainerCast. We'll catch you next time.
See ya.